Hi guys, my name is Vinay Jain and today we're going to be talking about depth first search DFS algorithm using recursion for general tree. So previously we discussed the same approach but for binary tree, where binary tree means every node has no more than two child nodes in the tree. However, general tree can have zero child nodes. Every node in general tree can have zero child nodes, one child node, two child node, or more than two child nodes. For example, here node A has three children, right? B, C, and H. If we take another example, let's take D for an example. So D has node C, node B, node E, node F as child nodes. If we take G for an example, node F and E are its child nodes, which is 2. So this is the case of general tree, and recursion is basically a function calling itself. So how do we compute depth first search algorithm using recursion for general tree? So for bookkeeping purposes, we'll mention here the child nodes of every node just for our sake of reference. So A has B and C as child nodes, B has A, C, D as child nodes, C has A, B, D as child nodes. Oh, by the way, A has H as well as his child node. B has four child nodes as stated earlier, B, C, E, F. E has two child nodes, B and G. F has two child nodes, B and G. G has two child nodes, E and F. Sorry, my bad. E and F. H has two child nodes, A and I. And I has, I'm just writing this here, I has two child nodes, sorry, one child node, which is H only. So now let's proceed with our algorithm. So again, we're gonna be using a recursion. I'll be drawing a tree here for better visualization, the same tree, but depicting how the depth first search algorithm works in terms of recursion. So let's say we have node A here. This is from where we're starting, right? So we first check for its first child node. First we check whether node A is our target or not. It is not, right? So we check for its child nodes, for all its child nodes. So its first child node is node B. So this is what the child node information is of node A, right? So we check for the first child node, which is node B. So we check here first. This is our first path. So we check if node B is our target or not. It is not. So we check then its children. For all its children, node B, what are the children of node B? A, C, D, E, right? Note that A has already been worked before and it has been added to the visited set. Let's keep a track of visited set. Sorry, I forgot to mention this. Visited set. So at the beginning, I'll start this again. So at the beginning, visited set would contain A in the beginning. And then when we traverse for all its children, let's say we traverse for all its children, node B is not there, right? So we traverse node B and also add it to the visited set. Now for node B, this is where we travel first. Node B, what are the neighbors for it? What are the child nodes for it? A, C, and D. So A child node has already been visited since it's already in the visited set. Therefore, we do not work with it. We check the next child node, node C. Node C is not in the visited set. So we add node C in the visited set and then traverse there. So this is our second path. The second path that we're taking. Now at node C, we check what are its child nodes, what are its neighbors. So C has neighbors A, B, and D. The first child node is A. So A is already been explored before since it's already in the visited set. Similarly, B is already in the visited set, but node D is not in the visited set. So that means we check node D next, which is in this direction, node D. This is the third step that we take. And add node D as well to the visited set, signifying node D has now been visited. Again, now we check for node D. What are the child nodes of node D? Node D has child nodes B, C, E, F. So it has child nodes B, C, and E, F. B, C are already in the visited set since they have been visited before. So with the next child node that we're actually going to work with recurs into is node E. So we move to node E. We move to node E and this is the next step that we take in our search for the target I. And we also add node E to the visited set. Now after node E, what are the child nodes of node E? B and G, right? Just a moment. Node E has child nodes B and G. So B has already been explored before because it's already in the visited set, but G is not. So the next node that we visit is node G. So we visit node G here and add this to our visited set. This signifies our fifth step in the DFS algorithm. Next, we check neighbors of node G. Since we're at that position, node G has neighbors E and F, which is here. E has been already explored before since this is the visited set. F has not been explored. So next we move to F. This is the next step in our algorithm where our algorithm works. So node F is now added to the visited set, signifying that this has now been visited. What are the neighbors of F? What are the child nodes of F? Child nodes of F is B and G. B has already been visited before since it's in the visited set, and so has been G. So now we cannot find anything here. So this then returns, since there are no more child nodes to explore, this then returns false to its parent call. Since it also has no more child nodes to return to explore, so it also returns false because it hasn't found anything yet from any of its child nodes. Node E has also found nothing from its child nodes, so it also returns false. Similarly, D returns false to node C. C returns the same result to node B. Node B also has explored all its children and hasn't found any match, so it also returns false to node A. Now node A checks whether it has any other unexplored child nodes or not. It has child nodes, node A has child nodes B, C and H, as you can see that here. B and C, they both have been explored because they are already in the visited set. But H, that has not been explored before, so it moves into that direction. So it next explores the H child node. This is where it moves next. Now when it has H child node, it checks whether this is the target value or not. It is not, so it checks for its children. How many children does H have? H have two children, A and I, as depicted here. A has already been explored before since it is the visited set, and I is not. So next it checks the I node. It moves towards the I node there. This is the next step in our DFS algorithm. Now it checks, is I the target that we're looking for? Yes, it is. So then this returns true because we have found a match, right? So this then returns true, signifying that we have found a match. Now H from checks all responses from its child nodes. If any of them is true, it returns true. So one response that has been recorded as true from the H child nodes. So this also returns true to its parent call. Now node A evaluates all child responses that it has gotten from its children. One child has responded false and the other one has true. So that means somewhere in the subtree of A, the node that we were looking for, the target I, that exists, and therefore this will also now then return true to its calling function. Sorry, my bad. So this is essentially how the algorithm works. To see the algorithm pseudocode, this is how it looks like. Algorithm for DFS using recursion for general tree. So this is the base case or base condition, or should I say stopping condition. Stopping condition basically to stop the infinite processing of recursion. So if we have a node null, if we end up in a null tree, then we return false. If we found a match, then we return true. Next, what we do is we create a set which is supposed to store all responses from child nodes of the current tree, of the current node. So, and then what do? We iterate all child nodes of the current node at step 4. What do we do inside of that? We get the child node that we're supposed to work with right now. We get one child node And if that child node is not present in the visited set, meaning that has not been visited before, we recurse into the left subtree. We recurse into the left subtree how? We pass the left node, left child node with the target that we're looking for, and we also pass the visited set so that the function knows what all sets have been visited before or not. So we'll recurse into the left subtree for, just a moment. When I say left node, I mean next child node. And this is also recurs into, not left subtree, recurs into child subtree. If we found a match in there or not, that response will be recorded in this child response, and we add this child response to our child response set, and then we check, have we received a true response from any responses from any child. If there is a single true response from any child, that means the node that we're looking for exists in the tree somewhere, and therefore we return true our calling function. If after iterating through every child node of the tree we still do not find any match, that means in the subtree of that current node there is no possibility of finding that target that we're looking for, and therefore return false. So this is the algorithm for general tree in which we are working with DFS traversal using recursion.